All right, so I want to talk about, well, basically Newton's third law problem that involves pulleys. There are two masses hanging over a pulley, mass 1 and mass 2. We're going to make a lot of simplifications here. A big thing is that this is, as always, a vacuum. There's no atmosphere to cause drag, okay, but we've been dealing with that all along. The other thing is this rope has to specifically be a massless rope. Can anybody tell me why the rope in these simplified problems, the grade 12 level, why would the rope have to be massless? What would a non-massless rope do to this problem? Ali? Yeah, you might have this mass here of rope and this mass here of rope pulling down on the pulley. That could be an issue. Different amounts of rope. Yeah, so if I have more rope on this side than on this side, then the rope might influence what's happening with the acceleration of the system. So the fact that the rope is massless, big issue. There's another issue with the rope. The rope also has to be unstretchable. Because if the rope could stretch, can you imagine that this guy here would dangle lower? And if it was stretchable, if this guy pulled on it, then it would just stretch the rope rather than actually moving the object. So this is also unstretchable rope. The other thing is that the pulley also has to be massless, because we've talked about inertia, and things that are moving in straight lines tend to go in straight lines and continue on in straight lines. Things that are sitting still tend to continue sitting still, but rotational inertia is another thing. Rotational inertia says that if things are spinning, they'll tend to continue spinning. So if this thing starts translating one way or the other, and the pulley starts spinning, and the pulley has a mass, can you imagine that spinning pulley is also going to contribute to the system moving somehow? So that's an issue. The other thing with the pulley is that the pulley has to be frictionless. Otherwise, we've got to deal with the pulley slowing things down. So we're making some big assumption here. But if I just throw it all out there, I'm not going to put all of our assumptions down on paper. We have a massless, unstretchable string hanging off of a pulley that has no mass and no friction, all the while in a vacuum. Can you accept that? Sure. Okay, why not? I got some other stuff to sell you too if you'll buy that one. But so this is just some simplification so that you can work through a problem. Obviously, we can throw friction into it. You want to throw a stretchable string into it, that's okay. Do it at university. You want to make your string have a mass, not a problem. It's a time-varying calculus function that you'll want to use, and you can do some integration and some derivatives as you go along doing it. I don't have a problem with that, but how about we save that for the professor, and the professor will be happy to explain it to you. The professor explained it to me. It was great. All right, moving on, though. I got to ask a question, otherwise what's the point of drawing this little picture? Here's the question. Find the acceleration of the system. Before we do that, though, we have to lay some groundwork. I want to start a free body diagram for each of these masses because I think that it's going to help me to think through some things. Well, I know it will. That's why I'm going to do it. So I've got mass 1 and I've got mass 2. What are some forces that are acting on each of these masses? Gravity, yeah. So I've got Fg, force of gravity acting on mass 1. I've got force of gravity acting on mass 2. What's another thing that's acting on each of these masses?
Each other?
Yeah, each other. We could actually say that there's force being transmitted, if you like, through the rope, imparted to the other object. Force of 2 acting on 1, right? Because this mass 2 is going to tend to go down, and mass 1 may tend to go up, and so that's going to be pulling mass 1 up. But at the same time, if there's a force of 2 acting on 1, what also has to exist? 1 acting on 2 and up. Some people will tell me that force of 1 acting on 2 is down on mass 2. Not at all. Force of 1 is resisting mass 2's motion. It's a reaction force. It's not driving mass 2 forward. So force of 1 acting on 2 is up on mass 2. Now, knowing that mass 2 has 6 kilograms of mass and mass 1 has 2 kilograms of mass, what direction is this system going to tend to go in? People talk about tendencies of systems like this. Is it going to tend to go to the right or to the left? Okay. And you know what I mean by tending to go to the right, do you? It's going to tend to sort of slump over this direction. So I'm going to call to the right positive and to the left negative. And if you want, we can label it up as positive to the right and negative to the left. But it's going to tend to go towards the right. And I can see that right off the bat. So now I'll get back to my question. Find the acceleration of the system. Now what we said before was we should really find the net force acting on the system. So I'll call it F net for the system. I could just call it F net. How could I figure out the net force acting on this system? Or what's going to contribute to the net force on this system? Ali?
Mass of the system times acceleration of the system.
Oh yeah, I could do that. I'm sorry. I was thinking about the vectors themselves. What are the external forces that would contribute to adding up to the net force? Yeah, so we could say Fg on mass 1 plus Fg acting on 2. Those guys would contribute to the net force of the system. They're external forces. I want to make sure that that's clear. It's the external forces that contribute to the net force. These tension forces don't contribute to the net force on the system. They just hold the system together. Okay? So they're not actually driving the system, they're just holding the whole thing from falling apart. I really should calculate what they are, and we have enough information to do it. Fg would be 2 kilograms times 9.81. Is there anybody that can do that in their heads? What's 2 times 9.81? Yeah, 19.62 newtons. 19.62 newtons. Now, if you want to make a note of this, is this pulling to the left or is this pulling to the right? Yeah, so that would be a negative value, wouldn't it? This guy over here, mass of 6 kilograms, 9.81 times 6 kilograms. What's that going to be? 58.86. Now, is that going to be positive or negative? Positive, because it's to the right, and we define to the right as being positive. Notice that we're not doing up and down as positive and negative. Tending to the right and tending to the left is your positive and negative. That's an important distinction. So now when I go back here and I do F net for the system, Fg1 is negative 19.62 newtons plus 58.86 newtons. And you would be shocked at how many people don't notice that negative sign. They'll just randomly add 19.62 plus 58.86 and they'll be like, oh yeah, it's somewhere around 80 or something like that. No. You got to keep track of the positives and the negatives. That's very, very important here. So 19.62, negative 19.62 plus 58.86. What do you get? Somewhere near 40. 39.24. Nice. 39.24 newtons. And then now I'll come back to Ali because she said we want to use the mass of the system, which in this case was just mass 1 plus mass 2, which is 8.00 kilograms. And Ali says we should use F equals ma to find the acceleration of the system, which will say A sys is equal to F net over mass of the system, or 39.24 newtons divided by 8.00 kilograms. It'd be close to 5.
4.95.
I like it. 4.905 meters per second squared. Now, if we want to round that off to sig figs, we definitely could. We could say it's 4.90 or something like that. I'm just going to leave it as it is. I'm going to leave it as 4.905 because we may use it later on. So the next part, part B, we'll follow the same pattern that we did with the boxes. Okay, let's find the net force on each individual mass on this pulley system. Okay, so I'll lay it out there. Here's the question, and you have it on your page. So part B, find the net force on each individual mass. Okay, and in this case, again, we could refer back to our free body diagrams, or we could go back to that F equals ma, that Newton's second law. We could say that F net for mass 1 is equal to mass 1 times acceleration, oopsie, I almost wrote it, I might as well, acceleration of the system, because the acceleration of the system is the same as acceleration of mass 1, because mass 1 is moving along with the system. And I could say that F net for mass 2 is equal to mass 2, again, times the acceleration of the system, because mass 2 is moving along with the system. And mass 1, we said, how many kilograms is mass 1 on? Again, 2 kilograms?
Yes.
So 2.00 kilos times 1.20 meters per second squared, and 6.00 kilos, again, times 1.20 meters per second squared. And 2 times 1.2 is, what is that?
It's 4.905.
Oh, 4.905. I'm on the last question. I'm sorry. 4.905.
That is 9.1.
Gee whiz. 4 point, I'm living in the past, man. 4.905 meters per second squared is the acceleration of the system. So 2 times 4.905. 9.81? Which just happens to be 9.81, which is what we're using as the acceleration due to gravity. Notice this is a force, that's acceleration. The fact that it happens to be the same number is just a coincidence due to the numbers that I chose. We really are not going to read any deeper into that than that. Just a coincidence in this case, I promise you. I really do, and I'm not trying to be like smart alecky or anything. It really is just a coincidence. So 9.81 newtons, and 6 times 4.905, what's that?
29.43.
29.43 newtons. All right. So that's the net force on each individual mass. Now, I would structure a question like this possibly to set you up for success in Part C, but you know the textbook doesn't always offer up a Part B like this. They might jump straight to Part C, and so you need to know that sometimes it's fruitful to just know what the net force is for individual masses. Because the next question that I would ask would be to find the tension in the rope. And when I say find the tension in the rope, you know that that's code word for finding what? Action-reaction force pairs, right? So in other words, when I say find the tension in the rope, what I really mean is find the force of 1 on 2, find the force of 2 on 1. And they should be the same value, but opposite in direction. The same magnitude, but opposite in direction. So I'm going to redraw those free body diagrams one more time. For mass 1, the free body diagram, I'll call it mass 1. And for mass 2, a free body diagram, I'll label it mass 2. And I'll label up all my forces. I should have force of 2 acting up on 1, force of 1 reacting up on 2, force of gravity on 2, and force of gravity on 1. And we know that these pictures, these free body diagrams, are just like a gateway to being able to set up equations for Fnet. Because really, this picture represents all the forces that go into making Fnet for mass 1. And this picture represents all the forces that go into making Fnet for mass 2. And so now that we have a picture and we know that fact, that this free body diagram really presents all the ingredients for making the Fnet equation, we could say Fnet 1 is equal to force of 2 acting on 1 plus Fg1, and Fnet 2 is equal to force of 1 acting on 2 plus Fg2. We have two equations. They weren't arrived at magically, they were arrived at mathematically. All right. But this doesn't get us to the final answer. What we want to get to is tension, and as we said before, tension is that action-reaction force between the two masses. So we have to isolate for that force. Force of 2 acting on 1 is equal to Fnet for mass 1 minus Fg acting on mass 1. And force of 1 acting on 2 is equal to Fnet 2 minus Fg acting on 2. And if we're going to go back and sub in our values, I just want to remind you that Fg1 was equal to negative 19.62 newtons, and Fg2 was equal to positive 58.86 newtons. We recently found out the net forces for each of these masses, so we can reuse those again, and we can sub in our values. Fnet1 was equal to 9.81 newtons, minus FG1, so minus a negative, because FG1 was a negative, negative 19.62 newtons. And over on this equation, we're saying FNet2, 29.43 newtons, minus, and I'm only solving this in parallel so that I can show a common result at the end, okay? Obviously, you wouldn't necessarily solve things in parallel like this. I'm doing this for comparison's sake. 29.43 newtons minus 58.86 newtons. And somebody help a fella out. What's 9.81 minus negative 19.62?
29.43.
What is it?
29.43.
29.43 newtons. And 29.43 minus 58.86? Negative 29.43 newtons. Holy moly. So force of 1 on 2 and force of 2 on 1 equal in magnitude, opposite in direction. And what we can say, now we'll use that language of tension force. The tension force is equal to 29.43 newtons. Okay, and when you say tension force, you don't have to say plus or minus, because it really just means the magnitude of force of 1 on 2, or the magnitude of force of 2 on 1. Okay? Because potato, potato means the same thing. Yes, sir? No, you could just find one of them, but for your own peace of mind, it's so easy to find the other one, and you would know that you get perfect. You know, isn't that a nice feeling in math class when they have these systems of two linear equations or something like that, where you get down to the end, and you can kind of self-confirm that your result was right, and then you get perfect on the test every single time? I love that. You should love it too. I mean, it's an opportunity, right? Take the opportunity.
And then sometimes you get it right on the check, yet everything's wrong.
Well, if you're consistently wrong about everything, then I don't know what to say.